Hello and welcome everybody to this Fabric Espresso. I'm joined again by Bogdan, which means we're going to talk about fabric. Today, we're starting a new series. We're basically going to talk about performance at scale with Warehouse in Microsoft Fabric. So, Bogdan, maybe again for the people that don't know you, a quick introduction and what we're going to talk about today.
Good morning, Bogdan Crivat. I'm a VP for Synapse Analytics at Microsoft, and I'm happy to talk to you today about what happens in Fabric.
Awesome. So let's head over to a few slides to dive a bit deeper inside the performance that we have in Warehouse.
Okay, so performance in SQL, performance at scale. We are talking about the data warehouse, a massive parallel processing software. So performance at scales here is basically the multiplication of a single node performance and the ability of the system to distribute the compute across multiple nodes. And how do we get a single node to perform really fast? It's a matter of optimizing the queries and then processing queries very, very efficiently, essentially dealing with data, reading data and analyzing data very, very efficiently on top of a single node. Now, it happens that inside Microsoft, we have access to the best pieces of technology for all these areas. We have the SQL Server Query Optimizer, which is the best optimizer in the industry. It's tested, developed over the last 20 years. We have vertipac, which is the fastest columnar query processor in the world, which originates from Power BI. And then we have Polaris, which is the most scalable distributed query processor in the world. It is the only query processor actually that has published a petabyte scale benchmark in the VLDB from August 2020. So we'll talk a bit how we do query processing in the new Synapse SQL, how we do query optimization, how we do multi-node distribution inside the new Synapse SQL. So let's start a bit with query processing. As I was telling you, query processing is about reading and writing data. And as you know, a big part of Fabric is that we committed to an open format. We committed to Parquet. Now, why did we commit to Parquet? It's an excellent format for analytics. It's a columnar format, meaning that data is organized column by column. And it's great for this kind of query. You see here, if I want to select the sum of quantity grouped by customer, all I need to do is to read the customer column, read the quantity column, and I can ignore product or any other of the potentially 800 columns that appear in this table. Now, it's not a great format for updates for transactions. For instance, if I try to execute a statement like this, update product and quantity where customer equals George, first I need to search the row number for George in the customer column, and then I need to go column by column and perform my changes. So again, Parquet is a great format for analytics, not truly a great format for transactions. So anyway, we were talking about Parquet. Parquet is first dictionary encoded. So you see in this column on the left, you have the string length for the product names. You see that all in all, we have 30 characters across this very small example. This can be 30 bytes or 60 bytes if you are going Unicode. The first thing that Parquet does is called dictionary encoding. It allows us to replace strings with numbers. So at the simplest, instead of having apples, oranges, pears, blah, 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 we are going to go into this number encoding that allows us to keep numbers instead of string in the product column. Now, as you may remember from your computer science class, a number has 4 bytes, an integer has 4 bytes. So basically, the full product column in this example is going down from 30 or 60 bytes down to 20 bytes because I'm replacing strings with numbers. But wait, you may remember again from computer science that 2 bits are sufficient to pack 3 distinct values. This is what's called bit packing. So instead of representing apples as an integer, a full integer, a 4-byte integer with the value of 1, we can represent it as 2 bits, right? And this is a new encoding. And in this new bit-packed encoding, the size of this product column becomes 10 bits, which is rounded up to 2 bytes. This is 15 times smaller than what we had in the original representation. Now, the third thing that Parquet does very well is called RLE compression. RLE stands for run length encoding. It is a compression algorithm that replaces repeated occurrences of the same value with their count. For instance, we have here apples and 1 and 1. With RLE, these are replaced with apples occurring twice and 1 occurring twice. So again, to summarize, Parquet takes your columns, it has a columnar representation, it performs compression through dictionary encoding, after which it applies RLE to make some of the columns as compact as possible. Now, again, a columnar format with dictionary encoding and bit packing and RLE compression. Those of you who may have spent time over the last 10 years to learn a bit about how Power BI work will discover that this is very much just like the Power BI vertipac format. Yeah, there are a few differences, but they're not dramatic. So now, given that Power BI vertipac also has column encoding and data link compression and bit packing, converting from parquet to vertipac is actually quite easy. We can read the data in the bit-packed format. We only need to translate a bit the dictionaries to re-encode them, and all of a sudden the parquet representation becomes the vertipac implementation, the vertipac representation in memory. And actually, the process of reading parquet as vertipac is so easy that it doesn't even require a full re-encoding. It's just a translation from one encoding to another. So we call it transcoding. And this is the core technology that allows us to read parquet as if it were a native vertipac. But it happens that vertipac can do a few more things. Vertipac has many operators like aggregation, filters, and group by designed to operate directly on compressed data. And this gives the fantastic speed that vertipac has today. Secondly, the code that can perform these operators is already available and ready to use both in Power BI and in SQL Server. You may know something that's called column store index in SQL Server. Well, that is a derivative of vertipac. So means that by reading parquet into this vertipac in memory representation, essentially by transcoding, we can use our best query processor engines directly on top of this data. Now, let's see what else is that we can use from Power BI. I was telling you that operators over run length encoded data are really, really fast. So how about we rearrange the rows to facilitate this RLE compression? You see, if I'm flipping these two rows, apples and pears, I'm going to get with 3 occurrences of apples, and all of a sudden, my RLE compression has a longer sequence here. Therefore, it is smaller, it is faster, it is better, all in all. So again, to summarize, how are we processing data in Synapse SQL? We read the parquet files, we transcode them on the fly into the SQL columnar index format or into the vertipac format for Power BI, and then we have the ability to use our best engines for fast data processing, both in SQL on the Synapse side and in Power BI. On the other hand, all the Fabric engines, SQL, Power BI, Spark, Custom, and so on, every time they're writing data in Parquet, they're performing the row shuffling algorithm that I was just describing for Power BI. And the result is Parquet files, which are perfect Parquet files. There is no aberration, no difference from the open source format, but they may have just a bit more RLE and longer RLE segments than you would expect. And this is what we call the V-order Parquet. It's basically Parquet where rows are shuffled in a way that optimizes for RLE compression. So in brief, this is pretty much what we are doing to accelerate query processing and to reduce the problem of query processing to our existing code, the columnar index in SQL and the vertipac code in Power BI. And this is it, folks.
Awesome. That basically shows you all the magic we have inside Fabric to actually optimize that data and make it go faster. Now, if you have any questions about it, make sure that you write them in the comments. We'll definitely get back to you. If you like the video, give us a thumbs up. And if you want to see more of these type of videos, just subscribe to the channel. There's loads of content on here. In the next video, we'll have Bogdan again, and we'll talk a bit more about query optimizations. But for now, this is Stijn from the Fabric Espresso team. And
this is Bogdan.
Thank you very much for watching. Bye.
Bye.